We are now ready to consider the first of two approaches of dealing with procedures. Let us take a look at the factorial function. It has an input parameter x and an output parameter y. In case x is greater than 1, it performs a recursive call using a temporary variable t for the output of that call. As before, the top-level call computes factorial of 3 and places the result in the variable z. The constructs used here are the declaration of a procedure with a formal input parameter and a formal output parameter and a command body, and a procedure call with an actual input parameter and an actual variable where the output is going to be placed. The basic idea is that at the call, the value of the actual input is assigned to the formal input variable, and when the call terminates, the formal result variable is assigned to the actual result variable. For the program at hand, we shall be generating the following program graph. The vertical edges in the left column will arise from the top-level program. The horizontal edges correspond to procedure call and return. The ones outside the dashed rectangle from the top-level call, the ones inside the dashed rectangle from the recursive call. And the black edges in the right part arise from the remaining parts of the body. We shall describe the detailed construction step by step on the following slides. We will construct the program graph for procedures at the point of declaration. A procedure declaration gives rise to two fragments of a program graph. A skip action incorporated in the main program graph where the declaration is made, and a separate program graph fragment for the procedure body using fresh nodes for start and end. To make this work, we will need an environment that for each procedure name tells us the names of the formal input and output parameters, the start node for the code of the body, and the end node for the code of the body. For a procedure declaration of a procedure P with input parameter X, output parameter Y, and body C, we will have the environment to map P to the quadruple X, Y, Qn, and Qx, where Qn is the start node of the body and Qx is the end node. The point of a procedure call is to create edges from the start node to the start node of the procedure body, as shown in the downward sequence of edges, and from the endpoint of the procedure body to the endpoint, as shown in the upward sequence of edges. Focusing on the downward edges, we use enter to create a new frame, and we declare new variables for the formal parameters x and y. We then assign the actual input to the formal input and make a record of the start and end nodes. In the assignment of the actual input expression to the formal input variable, we use a flooring construct that will allow us to deal with the problems arising if the arithmetic expression uses variables with the same names as the formal parameters. Focusing on the upward edges, we check that we follow a path corresponding to the actual call. We then assign the formal output variable to the actual output variable, and we pop the frame that was created at the call. Again, we use a flooring construct that will allow us to take care of the problems arising if the actual return variable was the same as one of the formal parameters. We have now explained the construction of program graph for declarations and procedure calls, so it is time for you to work it out on another example. Consider the Fibonacci function as defined here, together with a top-level call. Use the online system to construct the program graph. Explain how the various occurrences of the new actions are used in the program graph. In particular, the occurrences of record and check, the occurrences of variable declarations, and the occurrences of the special assignments using the flooring constructs. Having constructed the program graph, we need to explain the semantics of the four new types of actions. We shall begin with the assignment of the actual input parameter to the formal input parameter, where we're using a flooring construct. It differs from a normal assignment in that the arithmetic expression is evaluated in a memory where the top frame is disregarded. This is what ensures that no harm comes from the actual input parameter to use variables that also occur as formal parameters. At procedure return, we similarly bypass a top frame when looking for the variable to be updated. This is what ensures that no harm comes from the actual output variable to be the same as one of the formal parameters. Next, we introduce a special token star in the frames. A frame maps it to a pair of nodes in the program graph, one for the start node and one for the end node of the call. Recording a call simply creates a record in the top frame. Returning from a call, we check that we follow the edge whose pairs of nodes agree with what was in the top frame. This ensures that procedure calls return at the right points. It is useful to take a look at the program graph we created for the factorial function and trace through it and check that the memories at the various nodes are as shown here. This is something you should do for yourself right now. Once again, it is useful to redo this exercise on another program than the factorial, and we consider once more the Fibonacci function. Use the online system to construct the program graph and to expect the execution sequence produced. Explain how the frames evolve during the execution, in particular how memories are affected by the record and check constructs, and how the flooring constructs for input and output modify the memories. Having done this, you should read the section in the book, Doing the Try-It-Outs on the Way.